This is a brief demo of ECE542 project. The implementation we did was in Java, and it basically has 5 Java classes. The first one with which the user interacts is called the shell interface class. This is responsible for reading the command line arguments or reading the network.txt file from the hard disk. This internally constructs a network object. The network object internally consists of arc object and a node object. Each arc object is associated with cost and capacity. This is stored in a cost capacity tuple object. In the main method, we check whether number of command line arguments is 1 or 4. If it's neither, we print usage information informing the user that it either has to be 1 or 4 and give some details about what's valid. In case the number of arguments is 1, we go ahead and read the network.txt. If its arguments is 4, then we construct a random network based on the input. Let's first consider the reading from the network.txt case. Let's consider the example given in the project description PDF. In the command line, in this case, we would pass name of the text file, and the text file itself would look like this. So if we run, we get the output like this. It prints the network adjacency. So we store the detail of the network in an adjacency matrix. We next check if there is any cycle in the given network using depth first search algorithm with backtracing. The given example in this case is acyclic. If the graph is acyclic, then we go ahead and do a topological ordering of the network. Once we have done the topological ordering, we show the new network adjacency list. So this network adjacency list is different from the previous one. This is the network adjacency list for the topologically ordered network. We then calculate how much time we took to create the topologically ordered network, and then because it's acyclic and has no negative costs, we go ahead and apply the reaching algorithm, and we print the distance of each of the node from the start node. Let's next consider the case of a cyclic network with no negative arc costs. We'll consider the same example, except that instead of the arc going from 1 to 4, we'll have it go from 4 to 1, so that we have a cycle from 1 to 2, 2 to 4, and then 4 back to 1. So I'll make the corresponding change in network.txt, except that it's going from 4 to 1 here. I'll save this and then run. Okay, so now when we check whether we have cycles or not, it detected that this is cycle, and it found that there are no negative arc costs involved, so it's going to apply the Dijkstra's algorithm. Then as usual, it prints the distance of each of the nodes from the start node, and then it prints the time taken by the algorithm. What we found out was as we increase the number of nodes in the network, the time taken by the algorithm increases linearly, so it's big O of n. Let's next consider the case where we have a negative arc cost. So we'll consider the same graph again, and we'll make instead of 9, we'll make it -9. So we have a cycle with negative arc cost. The cycle is 1 to 2, 2 to 4, and 4 to 1. Because -9 is smaller than 10 plus 11, that's 21. Even though we have a cycle with negative arc cost, the cycle itself is not negative. So I've made the changes here to -9. I'll save this and then run. So it says it found a cycle at 1 to 4, but it did not detect any negative cycle. Then it says it has negative R cost but no negative cycle, so it will apply modified label correcting algorithm, and it will print the distances of all the node from the start node. Finally, let's consider the case where we have negative R cost as well as negative cycle. So instead of 9, we'll make it minus, let's say 29. So the cycle 1, 2, 4, 1 will be negative. So I'll make the change here to save it, and I'll run it. So now it says it found a cycle and found a negative cycle at 1 to 4 and back to 1. And it says one negative cycle detected. Because it has a negative cycle, uh, the graph cannot have shortest distances. Let's finally consider the case where we don't read the network from the text file. Instead, we generate it depending on the user input, the command line arguments. Let me change the arguments passed. Let's say we will have 4 nodes and 6 arcs and have some constant capacity. I'll save this and say run. So okay, in this case it generated a connected random network. This generated random network happens to be cyclic and does not have any negative costs. So we applied Dijkstra's algorithm and found all the distances. Let's generate a few more random networks and see if we can produce cyclic networks with negative costs. Okay, yeah, we got a cycle, we got a network with a cycle but with no negative cycles. So we applied a modified label correcting algorithm, and these are the distances of each of the nodes. And we'll generate one more random network. Again, we got cyclic with non-negative cycles. Once more, okay, we generated once more. In this case, we have negative cycles, and let's generate one more. Again, modified label correcting algorithm. Yeah, okay, we finally got an acyclic network generated. So it's acyclic, so we are applying reaching algorithm, and these are the distances.